In lesson 13, we're going to look at reflecting, shrinking, and stretching functions. So the first thing we're going to look at are reflections. So whenever we're thinking about reflections, that means there's going to be a -1 being multiplied through the function. The negative will either be on the outside of the function or it might be within that function. So if we think about our acronym HIVO, if we look at this first example, the -1 is on the outside. So we're multiplying the outside by -1, so the entire function by -1. So that means this is going to be a vertical reflection because vertical is on the outside. So if we flip an object vertically, meaning up and down, that means we're going to be reflecting over the x-axis. So this is a reflection over the x-axis. So this is a vertical flip, or flip vertically. So what happens is if we're flipping vertically, that means that we're taking our x comma y, so each of our coordinates, and we're keeping the x the same, but we're negating the y value. So that's another way of thinking of it. And then if you look at number two, the negative's in the inside, so this is going to be the horizontal reflection because horizontal is when you have the negative in the inside. So this is going to be a reflection over the y-axis. So this is a horizontal flip where you're flipping it horizontally. So for this one, you're going to take each of your coordinates and you're going to negate the x values this time and keep the y values the same. So those are our two rules for reflection. So remember, whenever you see a negative, that means there's some kind of reflection happening. Negative on the outside, flip vertically, negative in the inside, flip horizontally. It follows that HIVO acronym. So let's look at some examples of this. So for this first one here, I start with x squared. So we know that that's a parabola. There's our parent function. The vertex is at 0, 0. And this negative is on the outside. So this means I'm going to flip this parabola from being up to now flipping it vertically. So now it's going to be a parabola opening downward. And notice that the vertex stayed in the exact same spot because I'm reflecting over the x-axis. So the point on the x-axis or on the line of reflection is just going to stay on the line of reflection. This one here, if you imagine taking this original parabola and if you flip this part over the y-axis and you flip this part over the y-axis, you're going to end up with the same parabola you started with. So this picture is really just going to look the same as the original. And that's because parabolas are symmetric through their axis of symmetry, and the axis of symmetry here is the y-axis. So let's look at this set of examples. So square root function we know looks something like this. So there's our parent function. So if I want to do negative times f of x, that means I'm going to be flipping this vertically. So the original point here, 0, 0, is going to stay 0, 0, but everything else is going to get reflected over the x-axis. So again, remember, these are just rough sketches because we don't have grids, so we're just worrying about one point, just getting the general shape down when we translate these or when we reflect these, do any kind of transformations basically. And then when we're on a grid, that's when we're going to be more accurate. So for this one, this is going to be a horizontal flip because the negative's in the inside. So I'm going to take this original parent function. So here's my original parent function. And I'm going to flip it over the y-axis. So we don't really need our original, but just to show you the parent function, and then it was reflected over the y-axis. And again, you're trying to make these look as much as possible the same as the original. So the next page here, we just have some practice with this function. So here I actually already put in the parent functions. So the parent functions are all these dotted, the dotted graphs, just so that it's easier to do these transformations. So here's my absolute value function. And what we're going to do is we're going to do each one of these transformations to it. Now, some of them it's just one thing, but some of them it's a combination of a couple different things. So when I look at this one here, plus 3 at the end means I'm going to go up 3. So 1, 2, 3. I'm going to put my vertex, and again, this is just going to be a sketch, and there we go. So we're thinking about HIVO here. So if it's on the outside, it's going to be a vertical movement or a vertical reflection. Horizontal inside, so if something's in the inside, it means I'm going to be moving horizontally, and it means I'm going to be doing the opposite of what I think. So vertical, you follow what makes sense. So plus 3 on the outside makes sense to move up 3 towards the positive numbers. Here, we have a minus 1 on the outside, so I know it's going to be moving vertically, and because it's vertical, it makes sense. You follow what makes sense, so down 1. And then just redraw. This one here, we have horizontal inside. So since this is in the inside, it's going to be horizontal, and horizontal you do the opposite of what you think. So instead of 2 to the right, it's actually going to be 2 to the left. And I'm just always using that vertex here as my key point. And then because once I move that vertex, I can really just sketch the rest of the graph. So for this one, we have two things happening. We have this plus 1 in the inside, and we have this negative on the outside. So since we have this negative on the outside, that tells me that I'm going to be flipping this vertically, and I'm going to be shifting it horizontally. So I'm going to be shifting this to the left 1 unit because it's a plus 1. So it doesn't matter which one you start with here. I'm going to go ahead and I'm going to start with, okay, let's shift it left 1. And then what I'm going to do is I'm going to flip it. So take this, and if I flipped it over the x-axis, it's going to be a downwards V. So in this case, is a downwards V where I shifted it 1. So you could do this in 2 steps, but I just went ahead and did it in the 1 step. This one here, we have a horizontal shift, and it's going to be 4 units to the right. Over here for F, we have 2 pieces again. So since we have a negative in the inside, that means this is going to be a horizontal flip. But if you start with something that's symmetric and you flip it horizontally, it's just going to stay exactly the same. So if I take this piece and flip it, it's going to become this piece. If I take this piece and flip it, it'll become that piece. So this part here is pretty much not going to do anything because of this graph being symmetric to start. However, I do have the minus 2 at the end. So since that part's on the outside, that tells me I'm going down 2 units. And then the last 2 here. So here we have a reflection, a vertical reflection. So I'm going to flip it vertically. So this one's just going to come down. And this one's going to be a horizontal flip. So if I start with this piece becomes this piece over here. And this piece, when you flip it, becomes this piece. So since this was a symmetric graph to start, when you flip it horizontally, it stays exactly the same. So this page kind of incorporates shifts and reflections. The last type of transformation that we're going to look at, remember transformation is the big picture, and each one of these translations, which is shifting, moving around, reflections, and now stretching and shrinking, these are all part of transformation. So this is the last type of transformation that we're going to look at, stretching and shrinking. So when we talk about stretching and shrinking, again, there's 2 types of stretching and shrinking, just like when we're talking about reflections, just like we're talking about shifts. There's the horizontal and then there's the vertical. And both follow our acronym, HIVO. So it's exactly the same as the other. Remember, whenever you have your horizontal, whatever the notation is going to be in the inside of the function, and you're going to do the opposite of what you think. So if you're multiplying by a number, it's actually going to be getting smaller, and if you're dividing by a number, it's actually going to be getting bigger. Where vertical is when whatever the number is on the outside, and this is going to be the same as what you think. So if you're multiplying by a number, it makes sense that it would be getting bigger, where if you're dividing by a number, it makes sense that it would be getting smaller. So I've kind of already talked about stretching and shrinking by saying when you're multiplying by a number. So that's the biggest difference. Stretching and shrinking means that you're multiplying by some number. So you're going to see the notation is that you multiply by some constant. So that's how you're going to know if something's stretching or shrinking. You're going to know if something's shifting if it's adding or subtracting some number in the inside or the outside. And you're going to know if something's being reflected because it's going to have a negative, being multiplied by a negative. So if it's just being multiplied by some number, that means you're going to have some kind of shrink or stretch. So a horizontal shrink and a horizontal stretch is whenever you have this C in the inside and it's the opposite of what you think. So it's going to be stretching if C is a fraction, meaning C has to be between 0 and 1. We don't want negative numbers for this. So C is going to be between 0 and 1 because the negative just tells us that there's a reflection. So we're just going to say we're looking at the stretch as C being a positive number. And then it's going to be a shrink if C is greater than or equal to 1, or if C is greater than 1. If it equals 1, then it's not going to change any. So one thing though that is important to write down, that when you get a graph or an equation and you want to actually do a stretch or a shrink, what's going to happen is you need to change the x values if you're doing a horizontal shrink or stretch, because that means you're changing the horizontal pieces, which are the x values. So for these, the x values change, but the y values are going to stay the same. And basically think about horizontal shrinking and stretching as something is, if it's shrinking horizontally, that means it's getting skinnier, which means vertically it's actually stretching. If you stretch something horizontally, so that means something's getting wider and wider and wider. So let's say I have this parabola here. If I'm stretching this, that means it's getting wider and wider and wider. So here's my stretch horizontally. So vertically, it's actually shrinking while it's getting wider and wider because I'm pushing it down vertically so that it gets wider and wider horizontally, where a horizontal shrink means it's getting skinnier and skinnier and skinnier, but I'm stretching it vertically. So I would have to like pull it vertically, pull it up so that it gets skinnier and skinnier. So basically, a horizontal stretch is the same thing as a horizontal shrink. Or a horizontal stretch is the same thing as a vertical shrink. So just kind of keep that in mind, because in order to stretch something horizontally, you're actually shrinking it vertically. So this and this, these two things are equivalent, and these two things are equivalent. So when you look at the notation for a vertical stretch or shrink, the C is going to be on the outside, and you do what makes sense. So if it's a stretch, that means the C value is greater than 1. If it's a shrink, C is a fraction. And we're going to say that that means that C is between 0 and 1, because the negatives are just going to tell us that there's been a vertical flip. So we're going to only look at the fractions. So again, A vertical stretch is the same thing as a horizontal shrink. So that's why, if you look, both C values are greater than 0. And for stretch and shrink, those are the same because the C values are the fractions. So now for vertical shrinking and stretching, because you're doing something vertically, that means you're changing the Y values. So the Y values are going to change, but the X values stay the same. So let's look at some examples of actually how to use these. So this first set of examples describe the transformation of the graph of f that results in the graphs of g, h, and k given the following formulas for each function. So here's my parent function, x to the third. We want to figure out what happened. So looking at the equations, comparing. So the difference in g of x in comparison to the parent function is that I have this times 2 out in front. So since the 2's out in front, remember we're thinking about HIVO. Since the 2's outside, that means it's going to be a vertical. So is it going to be a vertical stretch or shrink is what I have to ask myself. Well, because it's vertical, it is what makes sense. So multiplying by 2 makes sense to get bigger. So that means it's going to be a vertical stretch by a factor of 2. And then for this one, 0.5. Okay, so it's on the outside. We say what makes sense for this. So 0.5, you multiply, it's really like multiplying by 1/2 or dividing by 2. It makes sense to get smaller. So it's going to be a vertical shrink by a factor of 1/2. And then this last one here, notice that, remember when we were doing this, we didn't, C is not going to be negative. C is going to be a positive number. So notice here that I have this negative as well as a 3. So the negative is going to tell me, so there's going to be two things for this. The negative is going to tell me that there's going to be a flip. And since it's on the outside, that means it's going to be a vertical flip. So if we're flipping vertically, that means up or down, so it's a reflection over the x-axis. So reflect over x-axis. And then the second thing that's happening is this 3 out in front, so that's going to be a vertical stretch because we're multiplying by a number bigger than 1, so a vertical stretch by a factor of 3. And then the last example is going to be now putting these on a graph. So looking at some stuff on a graph. So an accurate graph, not just a sketch. So this last example, we want to write the formulas for the functions that are depicted by these translated graphs. So basically what we need to do is the first thing we need to do is we need to identify the parent function. So when you're looking at these, first of all, these should all be going to the point 0, 0. So this graph here, if you want to just extend it, it should be going to 0, 0. Same with this one. All of these graphs should go through 0, 0. And basically what we then need to decide is which one of these is the parent function. So looking at this, I know that it's going to be the square root function because all of these graphs are in that shape of the square root function. So now I have to decide which one of these, so which one of these is actually represented by the square root of x. So the easiest way to do this is to look at some points. So my parent function, so PF for parent function, is going to be f of x equals the square root of x. So now looking at some points. So I know that they all go to 0, 0. So I'm just going to plot some points here. I know that this one passes through 1, 3. And Doesn't look like it quite goes through that one. It looks like 4, 6 is a point. So basically, I'm just going to put some points that it passes through. And then I'm going to go to this graph, same thing. This one goes through 1, 1, goes through 4, 2, looks like 9, 3. And then this graph down here, 0, 0, it looks like 4, 1. I don't really see any others. So looking at this, I have to figure out which set of points is satisfied in this. And right away, I see that this red graph has to be it. Because if you plug in 1 for x, square root of 1 is 1. You plug in 4 for x, take the square root of it, you get 2 for y. Plug in the square root of, or 9 for x, square root of 9 is 3. So this is going to be the parent function. So then the question is, how do I get these other graphs? So let's call this one g of x, and then we'll call this one down here h of x. So if we're looking at g of x, so let's start with that one. We'll find that. So with g of x, the first thing you want to do is you want to decide what did we do to the parent function to get to g of x. So g of x, what we did was if you compare the coordinates here, see how for these coordinates that I plotted, I have the same x values, but the y values changed. So we have the same x values, but the y values and the points that I picked, it looks like I multiplied by 3, but multiply y values by 3. So if I multiply the y values, that means I'm doing something vertically. So this is going to be a vertical stretch by a factor of 3. So when you go to write the equation, g of x, if it's a vertical stretch, that means that the 3 has to go on the outside, and it's going to be what makes sense. So if you're stretching by 3, in the formula, it should be a 3. So it's going to be 3 times square root of x, because you put that vertical stretch factor on the outside. So this is going to be 3 square root of x, and then you just keep the parent function. So then the last one here is h of x. So for h of x, we're going to compare. So if you look, the only point that I have plotted here is with the same x value is going to be a different y value. So if I look at this set of coordinates, we have the same x value, but the y values got half the size. So I went from 2 to 1. So, but the y values were divided by 2, or were multiplied by 1/2. So, but y values were multiplied by 1/2. Because if you look, if I look at the same x value, which this coordinate right here, so see how my x value is 1, but this y value is probably about 1/2. I don't know for sure, but it seems reasonable that it would be 1/2. Same with right here. It would be at x equals 9. This is at about 1.5, which is half of 3. So it looks like the y values are always going to be half the size. So we're basically just going to be multiplying those by 1/2 or dividing them by 2. So since the y values are the things that are changing, it's going to be a vertical stretch or shrink, but since I'm multiplying by a fraction, it's going to be a vertical shrink, which is why this is getting closer to the x-axis, where the other one's being stretched further up. So for this one, it's going to be very similar to g of x. The only difference is instead of a 3 out in front, I'm going to use the 1/2. And we do put it out in front because it's a vertical shrink. So then that's it. So that gives you your formulas. And again, using the grid, we're always more accurate and we can come up with formulas where when we're doing these on just a sketch, a set of axes, you can't be as accurate to come up with these stretches and shrinks, which is why we have to have this on a coordinate graph so we can actually look at specific points. But it is possible to sketch just based on knowing a formula and coming up with a generic sketch.